Hi, I'm Dr. J, and this is my guide to independence. Alright, of all the concepts we talked about so far, independence is probably the most important concept. Independence is an assumption that an analyst will make when analyzing data or analyzing a probability problem. And their ability to do the analysis often hinges on that independence assumption. And so it'll be important to be able to identify whether or not that independence assumption is reasonable for the application that they're using it for. We will see this idea of independence come up again and again when we talk about random variables, when we talk about discrete random variables and continuous random variables. There'll be a notion of independence for random variables in addition to the notion we're talking about today, which is independence of two sets. So, the independence we're talking about today is the independence between two events, A and B, and two events A and B are considered independent if their joint probability is the product of their marginal probabilities. If we want to write that mathematically, we write it like this. The probability of A and B is equal to the probability of A times the probability of B. Now, that's the simple definition. There's a number of consequences of this definition. The first, and one that makes it a bit more intuitive, is this one. If you want to write down the conditional probability of A given B, right? Last time we talked, or 2 times ago, we talked about that this is equal to the probability of A and B divided by the probability of B. If A and B are independent, then we can rewrite the numerator using the definition that we just provided, and that means that the numerator becomes the probability of A times the probability of B. Now we have the probability of B both in the numerator and the denominator, and so we can cancel those two out, just leaving the probability of A. Alright, so now this implication here provides a bit more intuition about what's going on with independence. So what we've written is that the conditional probability of A given B, that's the probability of A if we know that B occurred. So that probability is equal to the marginal probability of A. That is, even if we didn't know whether B occurred or not, that those two probabilities are equal. And so one way to think about this is that knowing B occurred provides us no information about whether or not A is going to occur. And that's what we mean by independence. Now there's a number of other implications that follow from this definition of independence. And if you want to test your knowledge about manipulating probabilities, you should verify that you can actually prove that these statements are true, given what we've talked about here in terms of the definition of conditional independence and what we've talked about on previous slides or videos. So here we just say that A is independent. So if A and B are independent, that means that A and B complement are independent, that A complement and B complement are independent, that A complement is independent of B. Okay? So all of those are true. So what this really means is that if you want to determine the probability of A, and I tell you that A and B are independent, then it doesn't matter whether or not B occurred. That is, it does not matter if B occurs or B complement occurs. That gives you no information about whether or not A is going to occur. Alright, so let's get to an example. So we're going to talk about rolling some dice. Now, statisticians and probabilists and data scientists like to talk about rolling dice, not because we think it's the most interesting of all possible things to be talking about, but instead because it's a situation that most of us are familiar with, and a situation that if you understand the concepts in rolling dice, that you can then have a start at applying those same concepts to many other real-world problems. So here we're going to be interested in what's the probability that my blue die right here is a 5, and that my red die right here is a 4. Alright, so those are the two events that we're looking at. Here they are. Event A is that the blue die is a 5 and that the red die is a 4. Man, I probably need some bigger dice here. Alright, so now the key assumption here that I'm going to make is that the two dice rolls are independent. That is, if I tell you that this blue is a 5, that does not give you any information about whether or not this red die is going to be a 4. And for most of us, that seems like a completely reasonable assumption. Alright, so if we make that assumption, then I say, well, what's the probability of A and B? That is, what's the probability that the red is a 5 and the blue is a 5 and the red is a 4? Well, we can just write that probability as the product of the two individual probabilities. Since there are 6 sides on this dice, each probability is 1/6. So we get 1/6 times 1/6, and we get a final answer that's 1/36. right? And that all stemmed from the assumption that we made that these two dice rolls are independent. Okay. All right, so let's talk a bit about some situations before we get there. All right, now let's talk about a slightly more complicated example, but still with dice rolls. We're going to allow the blue die to be any odd number, so it could be a 1, 3, or a 5, and we're going to have the red die be a 5 or 6. And now again, if we assume that the two are independent, right, that's the key assumption here. If they're independent, then we can find that the probability of those two events occurring, that this is odd and this is greater than or equal to 5, that is 1/6. Alright, now let's take a little bit of time and talk about situations that are clearly not independent. Okay, we're going to start out with dice rolls, then we're going to get to some more real world examples in a bit. Alright, so here's the first example. Let's say we have this blue die, and A is the event that it's a 5, there's the 5, right? And B is the event that the same die is a 4. Alright, now if you go back and talk about sets, right, these two sets are disjoint. Right? The events are disjoint. And what that means is that both a 5 and a 4 cannot be rolled on the same die in the same roll. Okay? So because both of those can't occur simultaneously, the intersection between these two events is empty, the probability is therefore 0. And if we now calculate the probability of A times the probability of B, right, it's 1/6 times 1/6, and we find out that's 1/36, and these two probabilities are not equal. Right? And that tells us right there that these two events are not independent, because by definition, if they were, these two sides would have to be equal. Alright, now let's add a little wrinkle into the scenario. So now I'm going to add a coin flip. So here I have a coin flip, and I have my die, and the key is that I'm going to say that what die I roll depends on what I flip on the coin. So if I flip the coin and it comes up heads, I'm going to roll a 4-sided die, but if I flip it and it does not come up heads, that is, it comes up tails, then I'm going to roll my normal 6-sided die. And so, rather than using the joint probability that we've been using so far, I'm going to use this time the conditional probability. So, if we rolled a heads, that means we have a 4-sided die, and so what's the probability of this event B, which is that we get a 6 on a 4-sided die numbered from 1 to 4? Well, the probability is 0. So the probability of B given A, that is, rolling a 6, if we got a heads, that's 0. If we now say, well, what's the marginal probability of B? So that is, what is the probability of getting a heads if we don't know what happened to the coin? Sorry, what's the probability of rolling a 6 if we don't know what happened with the coin? Alright, well, that's a little more complicated to figure out. It turns out that that's 1/12. You should check yourself and make sure that you can get that answer for the marginal probability of B. It might be helpful in this case to use the law of total probability. So now here the key is that because this conditional probability is not equal to its marginal probability, and in order for these two events to be independent, they must be equal, then these two events are not independent. Now, in this example, the two events were not independent because there was a causal mechanism between the two events. That is, the coin determined something directly about the die. In the next example, we don't have a causal mechanism, but instead we have a shared mechanism. So now we have our two dice, right? A red die and a blue die, and the event is that the red die is a 6 and the blue die is a 6. Those are the two events. But we have a third event of interest, and that's the coin. So here I'm going to call it D, and this event D is that the coin flip is a heads. And the key with this example is that what die we roll will depend on whether the coin flip is heads in this way. So if the coin flip is a heads, then the red die is going to be 4-sided and the blue die is 6-sided. But if the coin flip is not heads, then we're going to have a red die that's 6-sided and a blue die that's 4-sided. And so the key in this construction is that it should be clear that the events A and B can't both occur, right? Because each time we have at least one of the two dice that's 4-sided, and therefore we cannot roll a 6. So the probability of B and A both occurring is 0. Now if we calculate the marginal probabilities of each of these and multiply them together, and you should verify this for yourself too, we find that the probability of probability of A times the probability of B, in this case, is 1 over 144. And therefore, because these two sides are not equal, these two events, A and B, are not independent. and they're not independent because they have this shared mechanism that is the coin flip. Okay, so let's talk a bit about some of these shared mechanisms, but out in the real world. Alright, so oftentimes if we're looking at events temporally, that is in time, we will have a collection of events that are not independent. So a simple example of this is just that A is that it rains today, and B is that it rains tomorrow. Now these two events are generally not going to be independent, and they're not going to be independent because they have a shared mechanism that's typically, say, a storm front that's moving through. And so whether or not it rains today and tomorrow depends on whether or not that storm front is moving through. If no front is moving through, it's probably unlikely that it's going to rain either day. If there is a front moving through, then it's more likely that it's going to rain both these days. Right? And if I tell you that it rains today, that might tell you that, hey, there's probably a storm front moving through, and therefore it's more likely to rain tomorrow. Therefore, these two are not independent. Another similar example is a spatial relationship. So rather than collecting data in time, we're now collecting data in space. So as an example, we can say a real estate market. So imagine that we have two houses, they happen to be neighbors, and the events are that house 1 or house A, I guess the event is A, that house 1 has a list price that's greater than 300,000. And event B is that the neighboring house has a list price of greater than 300,000. Now, there might be some causal mechanisms here. That is, there might be a competitive advantage and one house is trying to undercut the other. But that's probably not the most dominant piece that's affecting whether or not these two events are going to be independent. These two events are likely not going to be independent because of, as we all know in real estate, it's location, location, location. Right? That location in large part determines the value of the house and therefore determines the list price for the house. And so if you have one house that listed over 300,000, it's probably more likely the other one will be, and vice versa. Right? And it all has to do with the fact that you collected the information and are looking at events that are spatially arranged. The next example has to do with clustering. So clustering here's my example. Let's suppose that a particular high school has a class in 2019 who had an average SAT math score greater than 600. And now what we're looking at for event B is whether or not the next year's class, that is the class of 2020, is going to have an average SAT math score above 600. And now there's some spatial aspects here because this is one school district, all the students are coming from some geographical area. There's probably also some temporal aspect because we're taking 2019 to 2020, but neither of those are probably the dominant piece that's at play here. Probably what's the dominant at play here is the fact that, hey, all these students went to the same high school, right? And therefore knowing that one class was above this average of 600 probably tells you that the next class is more likely to than they would have been before having that knowledge. And therefore these two events are not independent. Now, there are ways that we can statistically build models that account for these kind of mechanisms. They're still going to have the concept of independence, but then it will be a conditional independence rather than a pure independence like we're discussing here. Alright, so let's get back to an example where we have independence and we want to calculate some sort of more real-world probability. So here on this page, we're going to talk about the game of craps, which is a casino game where you're rolling 2 dice. And we're going to talk about just one specific roll, and that's called the come-out roll. The come-out roll, you win if you roll a 7 or an 11. So that's the probability we're going to try to calculate on this slide. We're going to use the idea of independence, but we're also going to use some of the other concepts that we've had previously in our videos. In order to calculate this probability, we're going to start with 2 simpler probabilities. We're going to calculate the probability of 11, then the probability of 7, and then combine those two. So, the probability that the sum of the 2 dice is 11 is, there's 2 ways for that to happen. Either the blue die can be a 5 and the red die be a 6, or the opposite. Okay? So that's represented here, the blue die being a 5 and the red die being a 6, or the blue die being a 6 and the red die being a 5. Alright, so now we have the probability of the union of 2 disjoint events. Right? We can't have red die being 5 and blue die being 6, and vice versa simultaneously. And therefore, by axiom 3, we have that this is the probability of 5, the blue being 5, the red being 6, plus the other probability. So this is true by the axiom. There was another way that you could have gotten here, and you could have gotten here by using the total law of probability, right? Where your partition was every possible combination of dice rolls. Alright, so now the key is we're going to have to assume something about these dice to calculate this probability, and in particular we're going to assume that they are independent. We're also going to assume that each face has equal probability of occurring, and between those two assumptions, we have that the probability of the blue die being 5, red die being 6 is equal to the probability of the blue die being 5 times the red die being 6. And the same for the second probability, or similar for the second probability. Alright, now we can calculate these probabilities. Okay, that one was due to independence. We can now calculate these probabilities. We have 1/6 times 1/6 plus 1/6 times 1/6, and we calculate that the probability that the sum is 11 is 1/18. Now we can go through a very similar process. We're not going to do it here, but we can find that the probability for the sum being 7 is 1/6. But this would be a great time for you to check your ability to manipulate probabilities and verify that in fact that is 1/6. And you're just going to follow exactly the same idea that we did here for the sum is 11. Now we're ready to calculate the probability we're interested in. That's the probability that we have a win in the come out roll in craps. There's two ways for this to occur. Either you can roll a 7 or you can roll an 11. These again are disjoint events. They both can't occur at the same time. So the probability of that union is the sum of the probabilities. Now we just calculate up above those two probabilities, and so we just plug them in and we find that the probability of winning in the come out roll in craps is 2/9. Alright, so this is an example of a real world probability, and it has to do with dice rolls. For those of you who know better ways to solve that, there are better ways to solve this, and we will be talking about those in the next few video series. Alright, so today we talked about this very important concept of independence. Independence, right, is that the joint probability is equal to the product of the marginal probabilities. We talked about a whole host of situations where this independence assumption is not reasonable and we'll have to be doing something more sophisticated. Right? And finally, we use this idea of independence to calculate this probability of winning in the come out roll in craps. In our next video, we're going to start talking about a series of videos that can calculate probabilities when you think that each of the individual outcomes are equally likely. These calculations involve a lot of counting. That is, you have to find the size or the cardinality of these sets that represent events. So we're going to talk about counting, talk about probability calculation. The application of these ideas are going to be to things like coin flipping and die tossing and drawing cards out of a deck and winning lotteries and so forth. So, until next time, I hope you have a great one.